of Mechanical Engineering Department, AD Patel Institute of Technology, a Constituent Engineering College of CVM University. I, Professor Baladat, welcomes you all on this final day of STTP on Applied Computational Fluid Dynamics for Engineers. Today, our session expert is Dr. Dipankar Bandyopadhyay, sir. Now, I would like to request Dr. Mitesh Shah, sir, to introduce our esteemed guest today. Over to Mitesh Shah, sir.
Very good morning to all and a very warm welcome to today's speaker, Dr. Dipankar Bandyopadhyay, sir, on behalf of Department of Mechanical Engineering of AD Patel Institute of Technology, Gujarat. So today is the last day for the Applied Computational Fluid Dynamics for Engineers Faculty Development Program, sponsored by the AICT AQIS scheme. And till date, I hope you must have enjoyed all the session. And today also, very good eminent speaker is delivering his talk. Before he starts his presentation, I would like to briefly introduce him. Bandyopadhyay sir is a BSc in Chemistry and BTech in Chemical Engineering from Calcutta University. After completion of MTech from the Department of Chemical Engineering at IIT Kanpur, he served as ANSYS Fluent India Private Limited for more than 3 years as a CFD engineer, before completing PhD from IIT Kanpur. Presently, he is a professor in the Department of Chemical Engineering and head Center for Nanotechnology at IIT Guwahati. He has also served as a visiting faculty at Yeongnam University at South Korea under the WCU program and KTH Sweden under the Erasmus Mundus program. His research areas encompasses thin film dynamics, soft matter physics, liquid crystals and smart materials, droplet and digital microfluidics, healthcare, point of care testing devices, MEMS, theranostics, microrheology, clean energy, harvesting, computational fluid dynamics, stability and instability of fluidic systems, complex fluids, microrheology, among others. He has authored 150 research publications in international journals and has filed 20 Indian and 7 international patents so far. He is also one of the PIs of the upcoming Center of Excellence on the Research and Development of Nano-Electronic Theranostic Devices at IIT Guwahati. He is the recipient of NCL's Professor K. Venkatraman ChemCon Award in ChemCon 2016. He and his group at the Indian Institute of Technology, Guwahati, is the recipient of the Gandhian Young Technology Award 2016 and 2019. BIRS's Dristy Appreciation Award in 2017. He is a nominated member of American Chemical Society, Royal Society of Chemistry, and Indian Institute of Chemical Engineers. Sir, we are very much fortunate to listen to you, and I am very much happy to listen to you, and it's my pleasure and privilege to hand over you now the mic. So please, you start your presentation.
Yeah, thank you. Thank you so much for the kind introduction. A very good morning to all the participants as well as the organizers. I hope I am audible, right?
Yes, sir, you are audible.
And I'm sharing my screen for the presentation. So I hope my screen is visible now to all of you. Am I correct?
Yes, sir, it is coming. Just a minute. Yeah, now it is fine.
So the first slide is there, right?
Yeah, title slide.
Yeah. Now, if you face any problem, you should immediately stop me.
Sure.
Okay. Yeah. So a very good morning to all the participants. I first thank all the organizers. You know, it's a very nice, weather in Guwahati. It's winter is just setting in. Okay, and I hope it's the same situation across the country. And I hope all of you are safe in this pandemic situation, and hopefully we will come out. We shall overcome, this unprecedented situation, maybe 2021, and my best wishes for that to all of you. So I just like to start the morning with something very unusual for all of you. And I understand that the audience is mostly engineering audience. And see, I mean, as I was introduced, I was just listening to that, 2000, I think 2000 to 2002, I was in ANSYS Fluent. And at that point of time, CFD was the buzzword. I mean, CFD was upcoming tool for the explanation of different types of engineering processes, or like, optimization, fine-tuning of different types of engineering processes. And maybe last 20 years, I have been one of those evidences who has seen, like, how a subject can evolve to a different direction. And that is what I'm going to show you today, that how exactly this particular computational fluid dynamics has evolved for the engineers in different applied fields. Okay, I will choose one. So, this particular topic of applied computational fluid dynamics for engineers, actually that fits in very well with the topic that we are going to discuss right now. So what we are going to discuss? We are going to discuss a very interesting and very, very different type of thing, which is called the electrorheology. Electrorheology of micro nanoscale soft assemblies. So first is the electrorheology, which will be a little bit new thing for you. And then we will see, like, the different aspects of micro nanoscale science and technology, how is it emerging, and how, like, this computational fluid dynamics is extending its domain of operation towards this type of engineering processes. Okay, it's very important to catch up with the time, and that's what perhaps is necessary for all these engineering processes that are emerging, say in last decade and maybe the next decade. Okay. Now I start with some basics. Next 5-6 slides are all simple basics I'm going to discuss, so that I can connect well to what exactly is the cutting edge right now in this area. So we all know that this is a typical random aggregate of any fluid, right? Now, so this is a random aggregate of any fluid. Okay. Now, say suppose if I start shearing, you may see a Newtonian fluid may get a kind of molecular assembly, something like this, right? But then, if you have non-Newtonian fluids, they may come up with some different types of assemblies, right? Now, say suppose if they layer-wise separate like this we call a kind of shear thinning. A shear thinning process, whereas if they cross-link like this, we may call this as a shear thickening process. So what is a shear thickening material? Say typically, like, quicksand, which in Hindi we call dal. So you may see that these quicksands, whenever you get into a quicksand, what happens? More you try to put force, more you get stuck. Now the science behind it, that, say when you are inside the fluid, now moment you are putting the force, you are trying to get out, so your body surface is generating shear on the fluid, and slowly you are getting chained up with the boundaries. More you put the force, more you will get, more you will be chained inside with the boundaries. A typical, action like this will take place. At the bottom you can see, so it's a random assembly of molecules between the shearing planes that leads to the shear thickening. Okay, whereas shear thinning is like suppose a kind of if some of you have painted the wall and all with oil paints, so there you will see there is a solvent, and then there are fillers, there are polymer molecules in terms of paint. So if you force on the wall, you may see that there will be layering of these polymeric molecules, And slowly, if you initially when you start painting, you will see that it will be a little bit difficult. But as you put more shear force, you will see that it will become easier because the solvent will separate out. So with very simple logics, without applying any of our engineering knowledges, just looking at the molecular architecture, I can really differentiate between three different very important domains of fluid mechanics. Okay, one is the Newtonian, the other is the non-Newtonian, and in the non-Newtonian, we can go for a shear thinning and shear thickening. This is part of the first slide that you plot that you see in fluid mechanics, but it's very important to have a molecular interpretation to that. Okay, and that's where the topic rheology comes into picture. So suppose a layering is taking place, basically the viscosity is going down with the shear rate. Whereas, if the viscosity is going up with the shearing, that means there is a cross-linking of molecules taking place. Now that is called shear thickening. And these are all physical processes. These are not chemical processes. These are all physical processes. That means moment I remove this influence of shear rate, what will happen? This material will go back to its original shape, right? So this is one very important aspect that you have to remember, that the external forces that we are applying, that play a key role in the response of the material. Now, there are microscopic, nanoscopic, atomic, or molecular responses, okay, which are small scale responses. Molecular atomic responses is the most fundamental responses. But at the level of micro nanoscopic, what happens? There is some sort of averaging of those properties. And then that is taken to the macroscopic scale. So the manifestations that we see in the domain of operation of engineering, which are macroscopic in nature, which are consequence of all these activities that are happening first at the atomic scale, then at the molecular scale, then at the nanoscale, and then at the micro scale. Great. Now, if we have elucidated this particular slide, then how do we interpret these parameters? Say as an engineer, you see, we start with the simple Hooke's law. Let's say suppose if I put a particular material under stress, okay, it will undergo a strain, right? And the stress and strain will be in phase up to the point I have the stress. It will either deform or it will either displace, okay, and the stress is proportional to strain. That is typically a kind of Hookean solid. Whereas the equation changes a little bit for a Newtonian fluid. So the stress is proportional to strain rate, right? So it has a time component, okay, associated with the stepped strain, and that's where you can see a kind of Newtonian fluid. And how do we test it? We test it, defining a kind of modulus G star, which is called the complex modulus, okay, which is by the stress star by strain. Now, what is G star? G star is nothing but G prime plus I G double prime. Okay, this I complex is kept for the time. Okay, since space and time are orthonormal to each other, so this G prime corresponds to the classical Young's modulus that you generally see, which originates from stress is proportional to strain, and this G double prime is nothing but the viscosity that you see from the Newtonian fluid, which originates from stress is proportional to strain rate, right? And the ratio of G prime to G double prime you can call as a kind of tan delta, which is the damping or the loss factor, which also has a consequence with the relaxation of a material, right? Now, how do we interpret? Say, suppose if I put a stress to a material, if it deforms, and if the strain is operating in the linear domain of stress to strain, there is a Hookean solid. Similarly, strain rate to stress, if I plot, then what happens? If it is linear, then that becomes my Newtonian fluid. And in between this Hookean solid is an idealization of the material. Newtonian fluid again is another ideal. These are two asymptotic limits. Most of the materials, now we realize today with all the characterizations that are available in front of us, we realize that most of the materials are not either Hookean or Newtonian. It is somewhere in the middle. Okay. So essentially what we have to study that, we may enforce some deformation through some force on a material. We may look at the response. Now, looking at the deformation to response, we have to compare that, this is what you have done to the material with the external force. This is what the response of the material with respect to the external force. Now, if I compare these two plots, from there I will be able to really see all the parameters. One is the stress, the deformation to the response, and one is the phase lag, and this phase lag is correlated to the time component. And from there, if I study these four parameters, which is the G star, the complex modulus, G prime, which is the elastic or storage modulus, tan delta, which is the damping or loss factor, G prime, which is the viscous or loss modulus, I'm more or less, I'm sure about how exactly the material behaves. Whether the material is Hookean, whether the material is Newtonian, whether the material is pseudoplastic, whether the material is dilatant, whether the material is rheopectic, whether the material is thixotropic, whether the material is viscoelastic, whether it's a solid viscoelastic, whether it's a liquid viscoelastic, okay, and different, or it's a Maxwell's liquid. So the different types of whether it's a creeping material, whether it's a material with recovery. So different types of information I can gather if I really characterize the material with respect to these four parameters, right? So rheology is the study. As I progress, I'm going to give you some more examples where we'll highlight that rheology is the study of measuring these particular parameters at different conditions of the material, like say suppose humidity, like say suppose variation of temperature, like say suppose influence of electric field, influence of magnetic field, okay, influence of different shear rates. So as the external forces change, how these properties change, that is what is essentially the study of rheology. Now, once we understand that, okay, what exactly is a transition from a simple to complex fluid, right? So whatever we have studied up to this point, whatever theories that we have developed up to this point, they represent this particular cartoon where these red balls are moving in a vessel. Essentially, if you remember the kinetic theory of gases, where we start developing this phenomenological correlation, like say suppose pressure is inversely proportional to volume, pressure is proportional to temperature, and from there you derive ideal gas laws, making some assumptions. So see, when you go for this type of phenomenological relations, okay, say suppose Hooke's law is also a phenomenological relation, Newton's law of viscosity is also a phenomenological relation. Okay, so these phenomenological relations are happening like, I'm doing 20,000 experiments, and from there I'm trying to derive a conclusion, which has no physical law behind it. I mean, we are basically trying to elucidate this from the observations. So more of a kind of correlation based situation. It happens like that. Of course, we can really rebut them with some scientific arguments, but at the end of the day, these are all phenomenological. That means a phenomena is taking place, and I can say that, okay, like Newton's second law of motion, like force is proportional to the rate of change of momentum, right? So this is a kind of phenomenological correlation. So those type of phenomenological correlations, they explain materials, which is shown in this particular box. Whereas in real life situations, you may all agree with me, so this may be a real life situation where, these balls are moving like this. I'm going to give you a more argument in favor of this hypothesis that, whatever our arguments that we are putting in the realm of Hooke's law, Newtonian fluids, okay, Newton's second law of motions, these are all very simple interpretations to the very complex process that is ongoing in the fluidic dynamical domain. And perhaps 2020 onward, you will see computational fluid dynamics is going to move towards that direction. Okay, and I'm going to show you one specific example in this particular lecture to convince you that, indeed that is the direction where like, the entire subject is moving towards. So you know that all Hookean solids are interpreted as springs, and all Newtonian fluids or viscous fluids are interpreted as dashpots. So springs are the places where the energy is stored, and the dashpots are the places where the energy is dissipated. So essentially, say suppose if you are forcing, if you are putting a force, this sigma can be any force. Generally mechanical engineering people, they try to put a load, a weight, a kind of stress, but then this stress can be any stress, like it can be an electric field stress, it can be a magnetic field stress, it can be a centrifugal stress, okay, it can be a surface tension stress. So any type of stress if you place on a material, if that energy is stored inside the material somehow, that means what? Say suppose I press the material, the energy is stored. If I remove the stress, then it gets its own shape back. So that is what is an elastic response to the material. Whereas if that energy is dissipated, just like if I pelt a stone in the pond, what happens after some time? Whatever kinetic energy the stone is traveling through, that is getting dissipated into the pond. So that's a typical action of a dashpot. An oscillatory response. What will happen? The entire energy will get dissipated and it will not be stored. So dashpot is a representation of a kind of viscous fluid, whereas spring is a response of a Hookean solid, and a combination of this is a typical situation of a viscoelastic material. And you can have different types of combinations, like say suppose this is a kind of series combination, right? This is a kind of series combination in parallel. Okay, so different types of combinations can be obtained for this to explain. Say suppose this is a dashpot model. Suppose this cross-linking is a kind of spring model, but if you combine these two, you end up getting something like this, something like this, something like this. And based on what happens, your constitutive relation change. What is a constitutive relation? Constitutive relation is the relation which is telling you, say suppose Hooke's law is a constitutive relation. Suppose Newton's law of viscosity is a constitutive relation. These are also phenomenological relations. So again, you are performing experiments with this system, a number of experiments with this system. And then you are looking at which pattern, you are making different types of theoretical models. From there, you are trying to identify, okay, this G fits in very well with this. And then you derive the constitutive relation related to this. And then that you put it in your equations of motions in order to describe the flow of this. Right? Now, this is a little bit away from typical Navier-Stokes paradigms where you already have assumed that it's a Newtonian fluid, it's like a water-like fluid, and then if you put a kind of stress or a kind of pressure drop, it is going to flow in a particular direction. Great. Now, so I hope I'm clear about what is a simple fluid, okay, what is a simple solid, and from there how exactly the definition of complex fluids are emerging, and our target is will be to interpret them from the rheological perspectives. Great. So now, what are the real life examples? So first example, I start with the most abundant material in your body, that is called blood. Now you know that our body is composed of 90% of water, right? So essentially, blood is also not very different. It's a water-based material. Okay, but I mean its major component is water, and then it's a kind of suspension water. It's basically an electrolyte. It's a very weak electrolyte. Okay, and then in that electrolyte you have different types of cells that are floating. Right? Now, if you take blood and if you start shearing blood, you may see a very interesting thing with respect to the response, with respect to the viscosity and elasticity of the blood. Okay, so this point is the viscosity and this is the elasticity of the blood. So you may see that, when the shear rate is very high, so the blood cells in the blood, they try and layer like this. Okay. Whereas when the shear rate is low, the blood cells, they arrange something like this, which is like a kind of, so you can see from high shear to low shear, there is an increasing, although the order of magnitude is about 2, but the magnitude may not be that high. So but you may see there is a gradual increase in the elasticity of the material owing to the arrangement of these blood corpuscles. Okay, and that depends on how exactly you put the shearing, right? And then you may see a kind of change in the viscosity also. Okay, although not significant, but you can see a kind of change in the viscosity also. So essentially, what you may realize that shearing of so the cellular arrangement inside blood is also dependent on the shearing, and the shearing need not be like you have to put a shearing from outside, but you may imagine that blood vessels are changing its diameter as it is going from the heart to the blood capillaries. And then, when the blood is becoming, blood vessels are becoming thinner and thinner, you may really imagine that the blood corpuscles are arranging themselves, self-assembling themselves in different organizations, leading to a kind of high or low shear flow and showing different types of behaviors like, say, dilatant or a kind of like pseudoplastic behavior. So the Newtonian blood can be although blood is a kind of non-Newtonian fluid, but in some place it may show Newtonian behavior, in some place it may show non-Newtonian behavior, and more importantly, it is not very wise to define blood in that sense. It is much better to define it in terms of the scientific parameters and the arrangement of the blood cells inside that. Right. Now, people are these days, I just wanted to deviate from the main topic a little bit for 30 seconds to tell you that actually this is a very good signature. This is a characteristic of a healthy blood. Now, this can be used for the detection of a disease called sickle cell anemia. Okay, where normal RBCs, they get distorted like this, and then their rheological behavior changes. Right? So now you can see that, you can really fit in different types of constitutive models for the blood vessels, blood corpuscles, which are like this. And then the blood corpuscles we are getting like that. And then, you can fit in, the blood, you can collect blood and you can run through and you can really see like, how exactly they change. And from there, these can be, say CFD now can be used in this situation for the detection of the disease. Right. So these are the different, dimensions that are now added, with the development of the subject, which is very, very interesting. All right. Now I want to do all of you an experiment that you take your finger and pull it. All finger may not work out, but if you just start pulling your fingers like this, you may see one of them will create a sound like tuck. Right, and this experiment we do, perhaps this is the most popular experiment when we are not when we are not doing anything. Perhaps this is the most frequently performed experiment that we sit down and we start breaking this create this breaking noise and all these things. Right. Now I ask you a simple question: what is the source of this sound? See, all of you are scientists. Some of you are accomplished scientists. Some of you are like very well-established scientists. Some of you are like budding scientists. Some of you are just starting. So I ask you a very simple question that all of you are doing this experiment as a scientist. Say suppose from the age of 5, 6, and say suppose you are doing this experiment for about 15 years. My simple question is, what exactly you are doing here? What is the origin of that sound? So you will find it's very interesting that any of the joints that we have possess between the bones, between two bones, there's a fluid which is called a synovial fluid. Okay. Now, what is the purpose of this synovial fluid is it reduces the friction. Basically, if this synovial fluid, if it is not there, those who are elderly, you may find that, those who are suffering from, arthritis, okay, you may find that the synovial fluid is not there between the bones, and that leads to very big attrition of the bones, the decay of the bones, and the decay of the nervous system that are surrounding the bones. Right? So essentially, the role of the synovial fluid is the reduction of the friction Basically, it's a lubricant in the articulating joints. Now, that is not the only purpose of a synovial fluid, but it also, this you have realized that, say suppose if you are like, hitting some surface, or if you are jumping, so you may see that your bones will not touch each other ever, right? Now, how does that happen? Because the synovial fluid is also a dilatant fluid. Now, more you press the fluid, what happens? It will develop these cross-linkers of molecules, just like I have shown for the blood. So, like, I will show you in the next slide that again you will get arrangements like this in between these bones. So during when you put this particular fluid into pressure, it develops cross-linking architecture so that your bone doesn't collide, in order to reduce the damage due to the collision of the bone. But moment you reduce the stress, they will thin to normal viscosity and resume its lubricating function. So in one end it is a lubricant, and on the other end it is a dilatant fluid, which is a kind of shock absorber. See the beauty of nature. Is such a. I mean, still today, with all the knowledge of different types of proportions, materials that are present inside the synovial fluid, the synthetic synovial fluid is perhaps another 50 years away before we will be able to really prepare one, and which is as good as this one, right? Not only that, the third purpose of the synovial fluid is that nutrient and waste transportation. So the synovial fluid actually gives oxygen and nutrients to your joints, and then removes carbon dioxide and wastes, right? And now you may just understand what is happening here after knowing all these things. That say, suppose when you are stretching it, what is happening? It is getting from a transition is taking place from the dilated to the Newtonian fluid, right? And then when you are releasing the pressure, carbon dioxide is generated, and the dilated fluid is undergoing a kind of failure here. Okay, now that is the reason when you are pressing it, first is the failure of the fluid which is in the middle. Whichever way in your body, whichever way, whenever you move, you should generate this type of sound-based joint decoupling of the joints. That is this particular thing is happening. That this particular fluid, which is a kind of like a fluid which is in one limit it is a Newtonian, and the other limit it is a dilatant. When the bones are very close to each other, it's a dilatant fluid. When you are releasing the pressure, it is thinning. And during the thinning, carbon dioxide is generated, okay? And essentially, the generation of carbon dioxide gas here, is leading to, the disjoint of this couple, and then from there, you are generating this sound. So very interesting CFD problem. You can see from here that there is a boundary, and in the middle there is a fluid. I can describe the fluid to you also. So essentially, you may see that this is the bone. This is the synovial fluid. Now, what is a synovial fluid? I have given you an architecture. Essentially, it is a electrolyte of protein. You may see there is water. There are different types of salts. Organic salts are there. Inorganic salts are also there. Then hyaluronic acid is there. Different types of proteins are there. So it's a very complex fluid, just like blood. But in one end, it is Newtonian. It's friction resistant. The other limit, it's dilated, it's a shock absorbent, and third is, it is also a carrier of nutrients. So you can see a kind of multi-purpose fluid, that has been generated. And just to tell you, all of you who are listening now, if you can synthesize this synovial fluid, you can be a billionaire. Artificial synovial fluids are in huge demand because old age arthritis, replacement, you can really stop this knee joint replacements and all if you can really design a very smart and long-lasting synovial fluid which can be injected in the joints, and then the joints can be made more fluid, right? Now, with this particular image, I am going to break another, misconception that you have. Let's say, suppose many of you go to gym and work out, and then many of you like to play cricket, football. But when you start the game, you are very fresh. Your all joints are moving very nicely. But when you finish the game, there is a fatigue, right? Now, generally, we say that the fatigue is because of the anaerobic, respiration that is going in the joints, and then the pyruvic acid, it's anaerobic respiration means pyruvic acid. The cells which are present here, they are undergoing like anaerobic respiration, and then pyruvic acid is getting converted to lactic acid, and that lactic acid deposition leads to the fatigue of the joints. And this is why a lot of lactic acid production, leads to what? Leads to the pain in the joints. However, you can also imagine that, say, suppose since this is a dilatant fluid, right? Now, if it is a dilatant fluid, if you put pressure on this, what will happen? You may have, cross-linking phenomena like this, right? If you keep adding more stress to your joints, what happens? They can be cross-linked temporarily. Okay, and if you are doing it for 2 hours, 3 hours, 4 hours, there can be heavy cross-linking, which may time to relax and get back to normal. Okay, that's a physical reason. We have performed some very simple experiments in our laboratory, and we have seen that this degree of cross-linking is there for synovial fluid. And then if we add lactic acid, actually this degree of cross-linking increases. So it's a combined phenomena of production of lactic acid. So lactic acid here, there are a lot of protein polymers here, right? Now these protein polymers, they cross-link and they create a network of structure in between the knee joints, which always leads to what? Which may lead to the fatigue. This hypothesis is not very, of course it is to be established, but we have a strong belief that in future we can really prove that this is the case. The other important aspect here is that, say, suppose this is a bone and suppose this is another bone, and say suppose you may see that there is a cartilage. So this basically you can expect that this is a kind of viscoelastic solid, this is a viscoelastic solid, and then there is a viscoelastic liquid, which is the cartilage. And then you have a synovial fluid, which is a dilatant fluid. This is the physical interpretation. Now, in this sort of situation, if you have electrolyte in the middle, and if you have two solid surfaces toward this side, and if you are undergoing friction for long duration, you may anticipate there is a generation of triboelectricity inside this chamber. What is a triboelectricity? You have performed this experiment for so long that, say, suppose you take a kind of two materials and you just undergo friction between them, and then you bring in terms of some other material, based on the electrochemical series. What will happen? They will undergo a kind of electrostatic attraction. So whenever we undergo friction, what happens? It generates a lot of electrons on the surface, and based on the electrochemical series, it may have a kind of Coulombic or electrostatic attraction. So suppose this experiment we have done, we have taken a kind of steel rod and brushed it with the polymer, and then we took small papers, cut the small papers into pieces, and then when we took this particular steel in front of that, then we could see that it is getting attracted, right? Now, so one thing this experiment tells us that if there is a kind of static system which is undergoing a friction with a fluid, it may generate statical electricity here, and it may generate also statical electricity here. Okay. Now, this statical electricity may also lead to assemblage of molecules, which I'm going to show you today. So essentially, I'm going from the basics of rheology to microrheology to electrorheology, and that slow transition I'm making with the physical systems that are in front of us. So what is electrorheology? Now I show you a video. So you may see the video. So what is happening? These are the two electrodes, and these are all pancreatic cancer cells. Now this work was about 6 to 7 years back. I think it was in Nature. So you have two electrodes, and these are the pancreatic cancer cells. So it's a cell separating unit. For a particular voltage, you may see that these cells, which are the pancreatic cancer cells, they undergo an assembly. So you may see that there is a chaining of the materials. The direction of the electric field is like this. So essentially, they are assembling, these cells are assembling. The flow is from this direction to that direction. It's a cell culture flow that you are doing. However, between the electrodes, you may see there is a chain-like assembly perpendicular to the direction of the field. This is the image. and these chains are getting assembled in between the two electrodes. It's a very interesting situation. Say suppose if you have a cell which is a kind of electrolyte in between and inside an electrolyte, cell which is a charged system having a zeta potential. Okay. Now say suppose if you are flowing into the system, what is happening? These cells preferentially for a given size range, it is getting preferentially accumulated near this. And now you can really analyze these cells very easily, which are otherwise very difficult to identify. Right? So what is micro and nano rheology? That these are the microstructures in a complex fluid. But say suppose if you change the log shear rate, what happens? These microstructures, they may undergo a kind of structure like this, they may undergo assembly like that, they may undergo assembly like that, different types of external forces. And that may lead to emergence of new properties, right? So now this is the framework where we are going to put up our experimental and computational fluid dynamic framework. Great. So in microrheology, what is electrorheology? Say suppose this is the assembly. This is a typical synovial system that we are thinking about here. So I'm just simplifying this architecture into this, that there are two surfaces. In between there is a kind of complex fluid. Now without electric field they are assembled like this, but if there is a statical electricity generated, there is a cross-linking. So this you can imagine as a kind of model mesoscale system where you may see moment the electric field is generated, these particles are getting assembled like this, there is a cross-linking, and you can imagine that this may be the reason for the immobilization of your knee joints, hand joints, okay, arthritic joints. This may be the reason for the immobilization of that, which is facilitated by the anaerobic respiration or the production of the lactic acid. Great. Now, up to this point, if it is clear, then we go to a very recent experiments, 2014. I'm going to show you now a set of videos. See, we have done the hard work, 10 slides of understanding what exactly we are attempting. Now we are going to perform some very smart experiments and then support it, analyze it with the help of computational fluid dynamics simulations. Okay, it's a very advanced system that we are going to discuss. Now, what is this? This is a microfluidic channel. This is a particle. These are the two electrodes, right? And then there is a flow that is taking place, right? And you have applied an electric field. See what happens. Sorry. So see what happens here. So you may see this particle is getting attracted to this electrode and coming back and making kind of recirculatory motion, right? And this recirculatory motion is leading to a kind of mixing. See, these are two fluids. You may see there is a dye here. There is another fluid. So you may see inside this. This is like a kind of rotor or impeller that is working here, right? What is happening here? So we performed a very simple experiment that you have a cathode and you have anode, right? And you put a single particle here. Now, if this particle is first touching the cathode, then this is, say, negatively charged. And now, moment this is a negatively charged, what happens? This is getting attracted towards anode. Now, once it is getting attracted towards anode, this is the motion. These are the typical times. So it is coming towards this. Now, moment it is touching the anode, what happens? Again, it is getting converted to plus. So it is getting attracted towards that. So you may see there is a movement back towards this. Essentially, this is what is happening. First, it is going there, touching here, getting other opposite charge, coming back, touching here, opposite charge, going back. Now, the angular way of this, providing this microchannel, is giving this circular motion, which is leading to this type of mixing. Right? So this is a very simple micro mixing experiment we started with. The first question that we asked, that if we put lot of particles into this sort of system, then what is going to happen? So essentially, this is a microfluidic channel. In that microfluidic channel, we have given heterogeneous sizes, glass bits of heterogeneous sizes, size distribution, typically 50 micron, average diameter 50 micron. These are the two electrodes. say microchannel, and we are flowing from, you may see that it is flowing from this direction to that direction, and we are looking from the top using a microscope. So you may see that these particles are moving incessantly, but then, if you look from the starting point, then initially the motion is there. Slowly, some particles are forming this chain, and these chains are, there's another chain here, right? So you may see this chain formation as the time progresses. Lot of molecule, lot of this, glass bits, they are under this incessant motion. Some are passing away. So our interpretation is that whomsoever is touching the electrodes, they are getting charged with the electrodes, and they are into this, to and fro oscillatory motion. And in the late stage, you may see that not all the molecules, but a group of molecules, they have assembled like this to create a bridge like this. And even this bridge is undergoing a movement like that, right? So now, what is this? So there is a chain. Now this chain, the upper part of the chain is moving in this direction, and the lower part of the chain is moving in this direction. So instead of a single particle, if we put a set of particles into the channel, we may see a kind of, we were trying to see like, what will be the electrorheological response in a fluid, filled with glass. We could see this sort of observation, right? Now, what is the interpretation? How is it happening? How are we going to really see the basic of what is happening? Let us start doing that. Now, simplifying the whole process, we thought that rather than creating a flow system, we go for a static system, right? So these are the two electrodes, and then you take a bunch of glass particles, and then you apply field and see what happens with respect to time. So this particular movie tells you what is happening over a period. Say this is time t equal to 0, but if I put glass particle under 6 kilovolt per centimeter, okay, you may see there are multiple threads which are joining like this. So essentially, if you look from the perspective of these two electrodes, there is a joining, right? But if you look at, from this direction, it is also layering. So one can really say that this is not only a kind of dilated behavior that is created in this direction, but also a kind of pseudoplastic behavior that is created here. So what is happening here? You may see that first, these are threads are being joined, and then wherever there is a gap, there is a kind of to and fro motion of these particles are taking place. You may see here they are coming, exchanging charge, going back, coming, exchanging charge, going back. And then where the density is very high, where this has happened for a very long duration, there is a kind of static chain that has formed, right? They are not always straight. They can be curved. They can be exactly like a straight line. They can be curved depending on different types of situation, which we will explain later. Now, what happens, if I go for a mixture of particles, say suppose these big ones are silver coated amberlite, which is about 900 micrometer, and then the small ones are the glass bits. Now here, see, if we mix it, so initially you may see that this bigger particles are getting aligned, and in between the bridges, there are smaller particles. So I was giving the example in the beginning that, say, suppose if you are a human being and if you are into a kind of quicksand and you are trying to go out, you may see that you are being chained. So essentially, you may see that these particles were like this initially. They were free flowing inside the microfluidic channel. But moment I put an electric field, now all these particles are chained. Here you may see that the chain formation is more or less linear. But here you may see that between two particles, a large number of chains are formed, right? And then, that is what is creating a kind of network. So in this place of the channel, I can expect that the fluid is Newtonian, but in this location of the channel, I can expect that the fluid has become dilated, right? So one can really see that this can be interpreted as two joints, okay, and this can be a kind of electrorheological fluid, and that is leading to different types of chain formations of heterogeneous particles. Great. So next is another experiment. So there is a debris here. there is a debris. These are all amber-like particles of different size, and see what happens. This is very interesting. You will see. So moment I start the experiment, what happens? They get attracted. Some of them go towards, so this is the anode. Okay, so it is touching here. The moment they touch the anode, they get charged. Now, whatever is touching the anode, this particular is touching that, that is touching that. So you may see that they are all getting aligned with this. Now you may see this one may collide with this at some point of time. Moment it collide with this, it is inducted into this line. Whereas this one is a little bit isolated. It is undergoing a to and fro motion like this. Whereas whomsoever has touched in this line to each other, they are just bouncing to each other, right? Now, very strange thing what was happening if I repeat this thing. So you may see that between two, say suppose I can understand that this is minus, this is plus. So as this is touching, this is becoming plus. Up to that point, this was minus. Now when it is touching, this has become plus, right? So I can understand that there can be an exchange between this and that. There can be a movement between this and that. But the question was why this particle is moving between these two. If I look at this, if I just focus on this, you may see that they are moving between these two particles. Now, why is that so? What is the reason behind this? Why this particle is restricting its movement between these two rather than moving like this, right? This is I'm going to explain as I progress. So, you may see that there is a kind of very interesting phenomena that is taking place, which we could uncover with the computational fluid dynamic framework. This is another system. I start from the beginning. These are all silver coated amber light. So you may see first it is touching, then this is coming. So this will touch. This will also touch. So you may see that this will also going to touch. So and then this touch, and then so in that process, you can see that there will be an assembly that is created by these, whereas these two are left out with no charge. Now, why did I quote silver? Just to increase the surface conductivity of this particle, whereas amber light, which is a polymeric resin, it will have less surface conductivity. Just to see that what exactly is the extent of assembly that takes place. So, with multiple particles, we could really get simple chain formation, to interpret what was happening inside that microfluidic channel. However, if you put multiple particles, the entire system becomes very, very difficult to explain what is happening. So what is the explanation? What is the origin? Why this is happening? In order to explain that, we thought that we will perform strategic experiments with two particles between the two electrodes, okay, which has a representative computational fluid dynamic system like this. So these are all axisymmetric and 2D simulations, because that these are all very costly simulations. Why? Because these particles are moving, means this will have a moving deforming mesh, right? And then these particles are they will have very thin separation distance between them, right? And then this particular domain requires as there is a charge exchange and all, it requires multiphysics. It requires the integration of the electric field, right? So we went for the two-dimensional axisymmetric model. These are the boundary conditions that are enforced, okay, whereas this is the experimental setup where we did put two particles in a microfluidic network, microfluidic channel, and with the two electrodes, and applied the field. So this has been published recently in Journal of Fluid Mechanics. So the next 10-15 slides is the story, what is the interpretation of what was happening there in the previous slides. So how exactly the CFD model has been taken? You know that for the fluid, we have the continuity equation and the Navier-Stokes equations. Okay. For the solid, we have the Newton's second law. This is the constitutive relation. This is the mass into acceleration, and we applied the electric field part. Now this is the Hookean solid, as we were discussing. This is the stress strain tensor, and what is the FE, total electric field force, is defined by. So this is the Coulombic. First is the Maxwell's force, that is tau, divergence of tau, leading to one which is the Coulombic, and the one due to polarization, and the polarization force looks like this. So this is the entire set of Newton's second law domain. This is the continuity and Navier-Stokes equation. And how did we get the electric field? We assumed it to be following Gauss's law, because this fluid was a dielectric fluid. These are the two electrodes. There was a very weak leakage current in the middle. Okay, and we did assume that there are charges on the surface. Okay, and then we solve for the displacement of the solid and fluid in order to get the total electric field between them. These E's are used in FE in order to calculate the FE. From there we got the displacement. From the displacement field, fluid structure interaction, implementing the fluid structure interaction, the motions of the particles have been captured. It's a complex system, I have told in a very concise manner in a single slide, because this may be a little bit boring for the audience, but this was about 6 to 8 months of work in order to really finalize and validate the model with the experimental system. So what did we saw with the two particle experimental system? So you may just see these are the plots of these representations only. So what is happening? So let us start from the beginning. Let us start from the beginning. So suppose this particle is here, this particle is here. The moment they touch these electrodes, this is minus, this is plus. So they attract each other. So you may see that they attract each other and they go there and they collide with each other, right? Now, moment they collide with each other, there will be a discharge, because these are all silver coated amber light. We coated silver, just make sure that the discharge is immediate. For amber light, the discharge will be poor. We have some results for amber light also later. You may see that the effect of the silver coating. Now, moment you have put the silver coating, moment they touch each other, they should be of same charge. Now, if they are of positive, say if they become positive charge, so both of them should move there. Or if they are negatively charged, both of them should go towards this direction. But we saw something very strange. What is that? Say after the collision, they went back to the respective electrodes, right? And then again they came back. So essentially, one can really see that there is a charge reversal that is taking place. So how do I interpret? I interpret like this, that when this is coming, this is plus, this is minus. So when this is touching, this is becoming plus and this is coming to minus. Now let us see the other particle. See, when this is coming, it is coming towards minus. Moment it is touching, it is becoming minus, it is going back to plus, right? So essentially, somehow these two particles are connected to these electrodes while the movement takes place, and there is a discharge mechanism that is taking place through these particles inside this in order to facilitate this phenomena. This is something amazing that has happened. Now, say suppose if these particle sizes are different, if these particle sizes are different, you may see the collision point changes. And this, you can see the collision type also changes. This was a little bit inelastic. Here you may see that this was more elastic. You may see that this is hitting like a kind of billiard ball. So you can see this, and you may see the collision point, which is for symmetric particles in the middle. The collision point was not in the middle, and they may undergo both of them may go in one direction. Okay, sometimes. So one can really see these are the different motions that are combined in the one with the multiple particles. So some more examples I give here. So these are the two amber light particles, and you may see here there will be joining in the middle, and then there will be a kind of the discharge time is a little bit more. Then after discharge it stops and then it goes back. So different types of combinations of those motions that we were observing for a multiple particle were resolved using this system. This is another example where one is silver coated, one is amber light, and of different sizes. So you may see this is another example where we saw that this is touching, and this touching contact mechanism is also changing. I mean, say suppose if this is big, very less amount of charge, a smaller but more amount of charge. So when discharge took place, after discharge, this was moving slower, this was moving faster. So different types of combinations were studied. So these are typical contacts. I just run 1, 2, 3, 4 for you. So you may see that the particle is coming. This particle is coming and then touching, and you may see that both are joined and going towards this direction for some time before it moves downwards or becomes stationary. These are two amber light particles. You may see that they join and they join together and they go towards the one of the electrodes for a while before this moves downward. So this is one silver coated, one amber light. You may see that they are joining. They are for a while they are moving, both of them moving upward, right, before it becomes stationary. Now you may see that this is a small silver particle, large amber light particle. They join and they undergo a kind of inelastic separation when they do it. So all these are happening in combination in that multiple particle to give that complex fluid dynamical phenomena and leading to that complex fluid property. Now the physical interpretation. So what we did, those governing equations we solved in COMSOL using finite element, right? So quadratic discretization was used for the flow field and displacement field and for the electric field variables, first order elements. Okay, momentum equations with streamline, using streamline and crosswind stabilization. You know that these will be extremely small time step. Okay, and then moving mesh boundary was used. Okay, mesh in the liquid domain was allowed to deform in a hyperelastic unit, smoothing and all. Lots of problems in terms of setting up the case and the time dependent equation. So now, since you want to make a kind of implicit situation, stable, situations rather than unstable situations in terms of time marching. So backward Euler and segregated solvers were used. Very interestingly, since I was working in ANSYS Fluent, this was a kind of heartbreaking affair to see that COMSOL multiphysics did give me the result rather than ANSYS has some issues with this multiphysics, integration of this equations from electric field. So coupling of electric field in 2 dimension is very good for COMSOL multiphysics, whereas for ANSYS, although 3D solver is very fast, but coupling of electric field became an issue, so we had to change our way towards COMSOL. And then we had used the time steps, adaptive time steps for to model those joining part. So this is your first computational fluid dynamics. After an hour, I think all are waiting to see some CFD. So you may see this is the separation of the 2 particles. Okay, so both the particles are considered to be of equal charge. So first experiment was collision and separation of 2 particles between the electrodes of equal charge, right? So this we could see that when they go towards the electrodes, they exchange charge. And how exactly you manage the charge exchange with the boundary condition. You define a separation distance here, you define a separation distance here, you define a separation distance here, and once the particle arrives there, what you do, you make sure that the charges are exchanged. You make sure the charges are exchanged based on the signs associated with that, based on the discharge associated with that. Those equations you cook up, and then you enforce in the computational fluid dynamics model first to replicate that 2 equal size charge particles. They separate and they join. Now, what is the next? Say, suppose if we make 2 different particles with 2 different sizes, right? So this was another situation, right? So you may see that in this situation, when we made 2 different sizes, in conditional cases, this was B, when the particle, so this is a particle 1 and particle 2. Okay, so particle 1 contains 20% of the theoretical value of the charge. I run it again from the beginning. You may see that during the initial separation, conditionally, this is moving downward. This is also moving downward. Before it is becoming stationary, it moves faster downwards, and this will slowly start moving upward, right? Now, what is the reason? What is the situation? What is the force contour? Why now you may see that this has started moving upward. So essentially, you may see that a rapid movement is always associated with more force, whereas a slow movement is associated with less force, and these are all Coulombic forces. So less force means less charge on the surface. More force, higher speed of motion means more force means more charges on the surface. So a less charge on the surface is creating a lesser Coulombic attraction between these 2, which is leading to a very slow motion, whereas more charge on the smaller particle, leading to a kind of faster motion towards this electrode. Okay, which is the major reason why it was moving fast, towards this, because then at that time it did not even discharge However, this was discharged, this took a charge from it and it started moving with a faster velocity, and that was the reason why it continued in this direction towards this. Right? Now, if you look at the force contour, it becomes even more easier. Say, suppose I look at 1 and 2 particle in between the 2 electrodes. So you may see that this top part of the particle will experience more force than the bottom part. Whereas for this particle, this part of the particle will experience more force than this part of the particle, right? So the movement, since it is an elastic material, so it will undergo a kind of, it's an elastic solid material, so it will undergo a kind of, there will be an average force associated with the cross section, which will enable the movement of this towards this and the movement of this towards that, right? Now, when they come closer towards each other, when they join each other, you may see that the other way around is when they collide with each other, what will happen? This part will have more attraction towards this, and this part will have more attraction towards that. But you may see that, you know, this is blue. That means this is, suppose this is negative. Okay, so this part will have more positive charge, and this part is red, means this is positive. This part will have a negative charge, and that is happening because of the proximity of the other particle. Say, suppose this is a blue particle, right, which is a negative one. Now, when it is coming closer towards this, what is happening? You know, during the charge reversal, you know, during the charge transfer, during the charge reversal, slowly the top part of 2 is becoming red, and the bottom part of the red is becoming blue. So there is a kind of charge reversal that is taking place, which is leading to, say, suppose when they join, say, suppose this is plus, this is minus coming. They come, moment they join, what happens? This plus becomes minus, this minus becomes plus, and then, you know, they go back. So this is plus, say this is minus, this is coming towards each other. Moment they collide with each other, this develops minus, so that, you know, this can go back, and this become plus, this can go back. Why this is coming towards this? Because this is attracted by this top. And why this is coming towards that? This is attracted by this electrode towards the bottom. Moment they collide, they undergo a kind of charge reversal. So now this is attracted by this, and this is attracted by that, and that you may see from the computational fluid dynamics force contours like this. Now I have explained this here, but it will be more clear here. You may see that in this situation, so it's a axisymmetric simulation, but it is put in a 3D form. So you may see what is happening. So now the bottom one and top one, after colliding, you may see there is a color change. So there is a charge reversal. And because of this charge reversal, so it is going back. So essentially, this bottom one was attracted towards this initially. So let me run from the beginning. This was attracted towards this was attracted towards that. Now, moment they touch each other, you know, now this will be attracted towards that, and this will be attracted towards this, and that is the reason why they go against each other. Very similar here. So, but then you may see here the phenomena of, like, say, suppose when they are closing in and when they are trying to join to each other, you may see that they may come together after the exchange of charge. They may migrate. This is attracted by this is attracted by that, and that is why these are done with they are coming closer towards each other. After touching, there is a kind of charge reversal. Now you may see that both of them are moving upwards a little bit together. Okay. Before, this is getting attracted faster towards that, while this will come down at the bottom. Now the color also shows that the charge is a little less, which is not allowing the enough Coulombic force to get attracted towards this. So we could explain, I'll come back to this slide. We could explain really the different types of, you may see that the particles are of different size, and their frequency of oscillation between the two particles are different, and their chaining mechanisms are very, very different. This one can really explain, you know, many different types of collisions and oscillations that are happening here that can be explained with the combination of these two particle motions to describe the multi-particle motions. Now, so while we analyze the computational fluid dynamic simulations, we saw something more interesting, that there are counter-rotating vortices around the particles too. Now, why this is so important? Because you may imagine that this is an axisymmetric simulation. So basically, I'm not allowing these particles to go away from the center line. So for that reason, I may see two spherical particles moving towards each other and going back, a kind of oscillatory motion. Each particle is having two counter-rotating vortices surrounding them. One can imagine that if I have a 3D simulation, which is very time-consuming and computationally costly, which we are attempting right now, if we can do that, one can very easily imagine that these vortices can not always be symmetric the way we have obtained in an axisymmetric simulation. Correct? So they can be asymmetric. Now, if they are asymmetric, one can really imagine that they may not move in a straight line, which we saw in most of the simulation. They may undergo a kind of distortion, and which you may see here. That is the reason why they are. So each of these particles, when they are oscillating, the first insight that we are getting from CFD is that they are surrounded by counter-rotating vortices. So that how many vortices are there, you can imagine for a chain like this. Now, in that, in some cases, this is straight. That means, the vortices are symmetric. Whereas in those situations where these are angular, where these are of different sizes, you may see that different types of, vortices that are created around this, which is actually opening up the proposition for micro-mixing while these particles are moving. And that may be the reason why you saw that Labonacci paper, had this mixing is not only because of the physical movement of the particle it makes, but each of these particles are carrying multiple vortices, surrounding them. And we could do a sensitivity like, we change the viscosity. So we could see that the circulation pattern as well as strength goes down. These are the vorticity plots. And we also did change the size. With the change in size, you may see that these vorticity patterns are also. So for a smaller size, you may see that, there are 4 vortices. Moment it is near the wall, there are 4 vortices. Okay, so these are all reproducible results, repeatable results when they are undergoing this periodic oscillation. See, initially it had 2, then they are coming closer towards each other, the vortex are getting stronger. Okay, and then when they are colliding and then bouncing back, okay, say now you may see that there are creation of these 4 vortices. And one can really imagine why these are happening, because now this is a circular particle moving in a fluid, because of the shape, it is enforcing the generation of these vortices, right? So, so one can conclude that yes, this type of assemblies are possible. This type of assemblies are possible, okay, and we can really explain with what is happening inside this. Now, I think, you can gain a lot of insight to what are happening between these two systems with the help of strategic experiments with simple 2 particles, multiple particles, and their assemblage under electric field. And hopefully that is the purpose by the organizers, to give you an exposure that what are the modern, developments of science and engineering in terms of CFD to explain different types of phenomena and improve your understanding. So most of the results that have been shown here, that is done by this small girl. Her name is Satarupa. So we are blessed with the support from different funding agencies. Okay, these are the acknowledgements. Thank you, and wish you a very happy New Year.
Thank you, sir, for this such an informative session on rheology and specifically part of CFD. Now, I would like to request participants to ask your queries.
Good morning, sir. Am I audible?
Yes, good morning.
Sir, you told that after doing exercise or playing games, there is a generation of lactic acid in our joints.
Yes.
So, this lactic acid is the same which is naturally present in yogurt.
Yes, pyruvic acid. See, if you look at your respiration, there are 2 cycles of respiration. One is called glycolysis and the other is called Krebs cycle. So glycolysis is associated with the generation of pyruvic acid, from glucose to pyruvic acid, that happens in glycolysis, and from pyruvic acid to carbon dioxide, that happens in Krebs cycle. So Krebs cycle is the oxygen, it's aerobic respiration, whereas glycolysis is anaerobic respiration. So during glycolysis, when pyruvic acid is generated, if you exercise hard, this pyruvic acid gets converted to lactic acid. During respiration only. I mean, since you are working hard, you are basically, allowing the cells to respire more, and in the process you generate in your body, you convert these pyruvic acids into lactic acid. And that is naturally generated and deposited in your joints to create those pain sensations.
Thank you, sir. Sir, I have another question.
Yeah.
Sir, for this same problem for the joints, sir, when astronauts go into the space stations and when they return, they can't walk because there is some gap between the joints of. So you said that the fluid between the joints convert into Newtonian from non-Newtonian. So what happened when they go into the space and return?
Yes, it is all low pressure situations, no? See, in space, you are basically, although you are kept in a very simulated condition, but then that is not natural. That is not atmospheric pressure, right? So the synovial fluid that are there in the joints, they respond to only the pressure and shear around that, and also to the statical charges around that, right? To my understanding, there is influence of magnetic field also, but that has to be proven. So electromagnetic field and the mechanical pressure around the joint, that is not normal in a situation when astronauts are there in space. So naturally, you can now correlate that with the discussions that we have for last 1 hour, that if you slightly change the condition, so the fluid will change in a different way. So the shock properties and friction properties associated with the synovial fluid will be different, and that will lead to any difference from the normal. You will have some sensation. That I think all of you have experienced that, if it is a little bit different, you have done something different. Say suppose you are standing on one leg for a while, you may suddenly have some pain sensation after some point of time. And that happens because of the change of the property of the fluid actually triggers the nerve responses. Okay? So that may be the reason what happens in the astronaut's case.
Thank you, sir.
Yes, any other questions from participants? Sir, as I have told you earlier that we have made this practice throughout this STTP, that if there is any query at a later stage from participant side, so the participants to send the same to me through mail, and I'll compile it and will send you the same if there is any.
Yes, please do that and send me one consolidated set of questions. I will answer them. Okay.
Yes, sir. So, on behalf of Mechanical Engineering Department, AD Patel Institute of Technology, I would like to thank our session expert, Dr. Dipankar Bandyopadhyay, sir. Thank you so much, sir, for sparing your valuable time and to give us in such insights. Now, as per my opinion, this is again very motivating for all of us to know that even for things which are there in our body and which we are dealing every day, they can also be closely studied and understand by CFD. So that is very motivating. With this, I would like to thank you, sir. Thank you so much.
Thank you so much. Thank you so much to everybody, and thank you so much for your attention. Have a nice weekend. Have a nice Christmas and have a nice Happy New Year. Wishes for a grand and healthy Happy New Year to all of you. Bye bye.
Thank you, sir. Same to you. Have a good day. So our next session, session 2, and on this final day of this STTP will be at